Hello and welcome to ENGR 330 Fluid Mechanics Recitation on Chapter 6. So as we have seen before, differentiation and integration was crucial in chapters 4 and 5. In fact, throughout this chapter, you'll see that more so in this chapter in chapter 6. Let's look at some problems. Determine the vorticity field for the following velocity vector. So the vorticity field is del cross V, okay, which is equal to, if you want to compute this cross product, it would be, you have to go back and remember how you did a cross product. Let me show that to you here. So you have dou x, you can write this gradient here, dou z, and then the u component of velocity, the v component, and the z component. Okay, and this is a cross product which you can compute. You're familiar with this, so let's go and compute it. So when you want to do the cross product, so first you do this, so the I component, so this multiplies with this, which is 0, minus this goes and multiplies with this dou by dou z of something which is independent of z, is like a constant, so that goes to 0. And similarly, if I want to do this guy here, it will be minus j times this guy, so again that is 0, minus this guy times this guy, and since this is independent of z, again that becomes 0. Okay. However, the k component will not be 0, it will have some value. So let's go ahead and do this. So as I said, I times 0 minus j times 0 plus k dou x of minus 2xy minus dou y of x square minus y square. Okay, so this is a simple differentiation you can do. So you observe that k times minus 2y plus 2y, so this is 0. So del cross v in this case is 0, so it's irrotational. Okay, so let's look at another problem. An incompressible viscous fluid is placed between two large parallel plates as shown. The bottom plate is fixed and the upper plate moves with a constant velocity u. For these conditions, the velocity distribution between the plates is linear and can be expressed as shown there. You're asked to determine the volumetric dilatation rate, the rotation vector, the vorticity, and the rate of angular deformation in this problem. So let's go ahead and do the volumetric dilatation rate, which is nothing but del dot u is equal to u dou x plus dou v dou y plus dou w dou z. Okay, so you can see that u is not a function of x, so this is 0. Dou v over dou y, there is no y component. V is 0, and W component is 0. So this is 0. Okay. In part B, you're asked to find the rotation vector. So the rotation vector, you can write the general form, which is half del cross V. The first two terms in this expression, like we have done before, will be 0 because there is no dependence on y and z, and or I should say there is no w and v component, and u is not dependent on z, and w is non-existent. So all we are left with, and I'll let you look at this formula, all you'll be left with is half dou v dou x minus dou u dou y, which is the k component of the vorticity vector. Again, this guy is 0. Okay, so what you end up is half minus dou u dou y, and we know the function for u, so this is a simple derivative. So minus u over 2b, the k component. Okay, so that's your vorticity, or sorry, the rotation vector. Okay, now we're asked to find the vorticity in part C. So vorticity is 2 times the rotation vector. We already determined the rotation vector before in the previous part, so this is nothing but minus u over b. Okay. If you remember in the previous slide we determined it to be minus u over 2b, so 2 times that will give us minus u over b in the k direction. Okay. Now let's go ahead and do part D, where we are asked to compute the rate of angular deformation. Okay, so the rate of angular deformation is denoted as that, which is nothing but dou v dou x plus dou u dou y. Okay, again this guy is 0, so all you're left with is dou u dou y, which is nothing but u over b. Okay, so you see that all you have to do here is to know the definitions for the dilatation or the volumetric dilatation rate, the rotation vector, how you get that, which is nothing but del cross V, and the vorticity, which is nothing but 2 times the rotation vector, and the rate of angular deformation, which we just determined. Okay, now let's look at the next problem. So for a certain incompressible flow field, it is suggested that the velocity components are given by the equations as shown. Is this a physically possible flow field? Explain. So for any physically possible flow field, we know that it has to satisfy the conservation of mass, or the volumetric dilatation rate should be equal to 0. So del dot V should be equal to 0, or it means dou u dou x plus dou v dou y plus dou w dou z should be equal to 0, and that's what we are trying to find. Is it equal to 0 or not? So let's go ahead and do it. So dou u dou x, we are given the function for u, which is 2xy. So if you do the derivative, partial derivative, this will be 2y. And similarly, dou v dou y, if you do it, it's minus x square. So clearly you see that it is not equal to 0, and dou W dou Z is 0 because the W component is 0. So definitely the answer is this physically possible flow field? No, because it doesn't satisfy the conservation of mass. Okay, now let's look at another problem. The velocity components of an incompressible two-dimensional velocity field are given by the equations u equals 2xy and v equals x square minus y square. You're asked to show that the flow is irrotational and satisfies conservation of mass. So for the flow to be rotational, we know that del cross V should be 0, and if it satisfies the conservation of mass, as we have done before, del dot U should be equal to 0, or the volumetric dilatation rate is 0. Okay, so cross V 0, and so these are the two things we need to check in this problem. Okay, so I'll let you do this del cross V, and you'll observe that it will turn out to be k times 2x minus 2x, which is 0. So it is rotational, and let's compute del dot V. So dou u dou x plus dou v dou y plus dou w dou z. There is no w component, and you can compute these two easily. So this is 2y minus 2y is equal to 0. That means it also satisfies conservation of mass. So it is irrotational and satisfies conservation of mass. Okay, now let's look at another problem. So it is known that the velocity distribution for two-dimensional flow of a viscous fluid between wide parallel plates is parabolic, that is given by that formulation with v equals 0. Determine if possible the corresponding stream function and velocity potential. So we are asked to find what is the stream function, what is the velocity potential. So for that you need to know how they are defined. So first let's go ahead and try to come up with the stream function. So if you want to do that, u is dou psi dou y, and v is dou minus dou psi dou x. Okay, and we already know that this is equal to 0, v equal to 0. Okay, and immediately we can tell from here that psi is not a function of x because it turns out to be 0, or which is what we are given in problem. So let's look at the u formulation. So we do the integral u dou y. Okay, and I'll let you do this integration since you know u. So just substitute in there and find the integral. You'll end up with uc y minus uc y cube over 3 h square plus a constant. The reason I put a constant here is we know that, if you remember in class, we decided that this constant will be a function of x, right? And since the v component is not a function of x, we can write this as a constant. Okay, so that's your stream function formulation. So let me write here that it can only be a constant. Okay, so let's look at to compute the velocity potential. So the velocity potential can be defined as dou phi dou x being u and v as dou phi dou y. Okay, again, v is 0. Okay, we should remember that. That's very important in the problem. And integral dou phi equals integral u dou x. So I can compute this easily as shown, and we'll end up with an integration constant which can only be a function of y. And you see that v has to be 0. However, dou phi dou y for the present formulation is not equal to 0. That means no velocity potential description is possible for this flow. Okay, so we could do a stream function, but we cannot do a velocity potential for this problem. Okay, which could mean that the flow is not irrotational, because if you remember in class we discussed that potential flows are ideal flows which are irrotational. So in this, let's look at the last problem. The velocity potential for a certain inviscid incompressible flow field is given by, as shown, where phi has the units of meter square per second when x and y are in meters. You're asked to determine the pressure at the point x equals 2 meters, y equals 2 meters. If the pressure at x equals 1 meter and y equals 1 meter is 200 kilopascals. You're given that elevation changes can be neglected and the fluid is water. Okay, so since the flow is inviscid, incompressible, and since there is a velocity potential description, that means the flow is also irrotational. So that would mean that we can apply Bernoulli equation along a stream line. Okay. Okay, so this would mean that it is irrotational. Again, I would encourage you to check if the flow is irrotational or not. Okay, for that, first you need to compute u and v, so I'll leave that as an exercise for you. Okay, so first let's go ahead and write the Bernoulli equation from going from point 1 to 2, and I'll call the 1 meter as point 1 and the 2 meter as point 2. Okay, so if the elevation changes are neglected, P1 over gamma plus V1 square over 2g will be equal to P2 over gamma plus V2 square over 2g. So at this point, we know P1, we know that we have to find P2, but do we really know these guys? Okay. Uh, the answer is we know because we know the velocity potential. So we need to compute the u from the velocity potential, okay, which will be given in terms of x and y, and similarly we compute the v component, which is 2x square minus 2y square. Okay. Now we know that v1 square will be equal u1 square plus v square, v1 square, and the subscript 1 here denotes that it is x1 y1 square plus 2 x1 square minus 2 y1 square. Okay, so you can go ahead and compute it. It will turn out to be 16 for x1 y1 to be 1 comma 1, and similarly we can do v2 square and it will turn out to be 256. Okay, so now at this point we know v1 and v2, the only unknown is p2, so we have one equation, one unknown. So make sure you get the specific weight of water from the tables in the front of the book and substitute everything and make sure you're consistent with the units. And P2 is 80 kilopascals. Okay, so this is a nice problem where they didn't directly tell you that the flow is irrotational, which should be the case when you want to apply the Bernoulli, but they gave you a velocity potential description. So if you remember in the previous problem, the reason we couldn't come up with the velocity potential description is the flow will be irrotational if you go ahead and compute it. But in this case, the flow would be irrotational. I think I said, okay, in the previous problem, the flow was rotational. Okay, so that's the difference. Okay, so still have questions, we can discuss this when we meet during the recitation, face-to-face meeting. Otherwise, good luck and see you next time.